Good evening, ladies and gentlemen. We'll get started in just a couple of minutes. If you can write something in the chat, so I know that you're there and you can see the live stream, that would be awesome. Thank you. For the chat, you likely will have to create a channel. If you don't already have one, just create a channel and go back to the YouTube live stream. Hi, Scott. Hi, Miss Michaels, Sita. Hello. Okay. Good evening, ladies and gentlemen. I will be sharing a short presentation before we get started. Welcome to MehtA Machine Learning Conference, Summer of 20 for high school students. A little bit about myself. I am the instructor of ML Bootcamp. I graduated with a bachelor's and master's from MIT a couple of months ago. I was actually planning to go on vacation before I started for full-time work, but then the pandemic happened. And high school students told me about summer camps and internships being canceled. So I thought, why not offer a machine learning bootcamp course, since I was very passionate about machine learning, and a lot of people are often curious about what AI and what ML is. I was received with support as well as skepticism. Some people were super excited and some people were a little nervous about high school students learning machine learning. Will they be able to grasp it? The math is complicated, the coding is complicated. And it's summertime. People like to have fun, not do machine learning. So, and to be so many hours on Zoom, but you be the judge. And let's see if high school students can do machine learning. A little bit about the camp. We met for 6 weeks virtually. We met for 4 hours per day, Monday to Friday. We met 9 a.m. To 1 p.m. Chicago time, but for some of our students, that was 3 a.m. And after class each day, we would have office hours with teaching assistants, and they would be available on Slack round the clock so students could ask questions anytime. We covered a lot of artificial intelligence and machine learning concepts, as you can see here. And we also taught students Python and Python machine learning libraries, as well as web dev skills. We introduced to them good coding practices, like using different text editors, using a virtual environment, terminal, command line, and how to use GitHub. We also discussed the ethical implications of machine learning and taught them soft skills. Students were assigned homework, unfortunately, even in summer, every single day. They solved mathematical machine learning problems, which often involved complicated concepts such as calculus and linear algebra. They were taught coding and they had to apply that for their homework, where they worked on data pre-processing and creating different machine learning models. They read papers in the field, and they also implemented some of the models from papers from scratch, using no existing code whatsoever. Students completed a mini project generating text using neural networks. So some students chose to generate tweets, headlines, college emails, while others chose to extend Shakespeare plays and the classic texts. And at the end of the boot camp, the students were supposed to apply their skills in a final project. The students selected their own teams and their own project topics, which was very interesting because our students had not met each other before. So virtually they connected with each other. You know, this was run like a college level class where it was very much student-led and project-based. This class is specifically the Fabulous 40 because we have 40 students. We had 5 freshmen. Some of them were homeschooled, some of them attended high schools. All over the nation as well as the world. We had 8 sophomores, 8 juniors, 13 rising seniors, and we also had 5 college freshmen that will be attending Harvard, Carnegie Mellon, University of Toronto, and Brandeis University. We also had a college sophomore from Vellore Institute of Technology. Our student distribution, we had 60% females attending the camp and 40% males. And we were from all over the world, as you can see, US, Canada, Bahrain, UAE, India, South Korea, China, and Philippines. And of course, the most important thing of today, let's wish Ishita a very happy birthday. Student distribution, we had 60% females attending the camp and 40% males. Apologies for the feedback. So Ishita, maybe isn't this the best way to celebrate a birthday from a machine learning conference? So please do join us in wishing Ishita a very happy birthday. I wanted to especially thank my mentors, Professor Anand Chandra Kasan, who's MIT Dean of Engineering and was my PI. His Super Europe program inspired me to make this machine learning bootcamp. I wanted to thank Dr. Young Lu, who was my mentor at Argonne National Laboratory, who taught me the importance of researching and writing papers. I wanted to thank Mr. Anshul Mittal, who was my mentor at Amazon Audible, who taught me how to work with big data. A thank you to Dr. Murdoch, who was my mentor at HealthJoy, who really taught me how to present myself. I want to thank Ms. Christy Riken, who was my AP Environmental Science teacher and who inspired me to be an engineer, and Dr. Sapan Shah, who guided both my brother and me throughout our high school careers. I wanted to especially thank our guest speakers, Kavya, Anna, Mr. Gangadharan, Simran, and Venkat, who all talked about the applications of machine learning in the work that they were doing. Special thanks to Dr. Bopana, Dr. Kim, Ms. Reitmeyer, Ms. Patel, Dr. Wallace, Dr. Jensen, Dr. Chituri, and Ms. Zimlowski for letting the world know about this bootcamp. And special thanks to our TAs who work day in and day out, Ms. Marva, Ms. Andrea, and my brother, Mr. Bagirith. And of course, last but not least, special thanks to our parents, who without them, it would have been very difficult to run this bootcamp because of your continued support and guidance. I think students were very successful in their projects. So without further ado, I would like to hand over the mic to the MC of this event, my brother and TA, Mr. Bagirith MehtA.
Welcome, everyone. I'm Bagirith MehtA, your host for tonight, and we're going to get started soon. But first, some housekeeping tips. We'll be delving into some heavy topics tonight, a lot of artificial intelligence and machine learning models. So I'll be telling some jokes between presentations just to keep it a little light. It's going to be a little challenging, though, because we are on a 20-second delay from the live stream. And as we all know, a key part of comedy is
timing.
Thank you. Exactly as we practiced. Because of the delay, if you have questions you want the presenters to answer after the presentation, please type them as soon as possible in the chat so we can get to them in time. We will take up to 2 questions per group to keep things moving along. And if time permits, we may open the floor up to more questions at the very end. If you need to sign in and create a channel in order to comment on the live chat on the YouTube stream, please do that as soon as possible. And now let's get started. First up, we have the team Seamless Stairwells, putting the ML in Seamless and AI in Stairwells, presenting their project on handwriting recognition with convolutional neural networks on writings by George Washington. Take it away.
We can all hear you, Ryan.
Hi, my name is Ryan, and I am a rising junior at Lake Zurich High School in Lake Zurich, Illinois.
Hi, I'm Doug. I'm a rising senior at Maine East High School, and I'm from Chicago.
Hi, I'm Peter Terpstra, and I'm homeschooled and live in Chicago.
Hi, I'm Jaydev from India, a sophomore at Vellore Institute of Technology.
Our project is handwriting recognition with convolutional neural networks. The project's motivation was to be able to differentiate accurately between various handwriting authors, in this case, historical versus modern authors. Usually, author determination is done by humans by comparing visually between handwriting. However, many of the things you need to look for require special training, so the question machine learning can make the same skill accessible to more people. Thus, we decided to make an AI to do that, so that anyone can give it handwriting and it can identify who wrote it.
We used the following datasets: the IM Historical Handwriting Database and IM Handwriting Database. There was a significant data imbalance because the IM Handwriting Database contained 13,353 lines, whereas the George Washington database contained only 656 lines. We fixed this by randomly sampling 20% of the handwriting database, leaving about 2,500 images to make the data more balanced. The IM Historical Database, which had the George Washington handwriting text, didn't require any pre-processing because it was noise-free and normalized already. We chose this dataset as this was the largest database of single historical figures handwriting available to us. For the IM handwriting database, which had the text from various authors, required pre-processing. The pre-processing included to change the threshold value so that the background would be white while the text would be black. And next, prior to changing the threshold value, we also grayscaled it because the George Washington database was done so. The size of the image was not a problem because the model cropped it into numerous 113 by 113 images.
These cropped images were then passed as batches of input into the model. Our model implemented a convolutional neural network, which is a type of deep learning network which is best at classifying images. The data was passed through 3 convolution layers, which recognize patterns of pixels in the images. The data was then flattened and fed forward through 3 densely connected layers with output sizes of 512, 256, and finally a binary output layer which returned a value of 1 or 0, corresponding to whether or not the sample was written by George Washington. The model was trained for a total of 8 epochs with 750 batches of images every epoch. Below, you can see a sample of the many correct classifications the model was able to make. I'll now demonstrate the model classifying some images. This image is a sample from the George Washington database of a handwritten line written by George Washington. Here in this code, we've loaded the model with the weights that we trained it that were trained to it, and then we load the file path of the George Washington image to the model, and when we can see that it predicts that it was in fact written by George Washington. In contrast, this is one of the already pre-processed IAM handwriting images, and when we pass that to the same code, it does the data augmentation, and then we predict on it, and we can see that it was not written by George Washington. This was consistent for almost all of the tested data images. It doesn't look like Peter...
Oh, sorry, I was
Peter?
muted. After training the model for 8 epochs, we got a testing accuracy of 99.7. While this is quite high, we consider it reasonable due to the fact that we had a large amount of data and our efforts to prevent overfitting. While 8 epochs may seem like not long enough for training, it was trained on hundreds of batches, with each batch containing many cropped images, meaning each epoch it saw thousands of images, so 8 epochs was plenty of training.
Many might be asking what applications handwriting recognition might have in the future. Well, the task of identifying a writer through handwriting inspection is very hard, especially when the inspector lacks the experience to do so. Using machine learning to do the same task is more simple. As seen through our research using CNNs, we were able to accurately predict 99.7% of the time if the author was George Washington from the handwriting sample alone. With this, we proved that machine learning is able to very accurately classify handwriting samples based on whether or not they were written by historical figures. In the future, with access to more data, we would like to expand our model's capabilities to identify more historical figures. The research in this project could be extended for purposes like fraud detection, handwriters' age determination, and time period of writing. There are many possible applications of handwriting recognition, historical and otherwise, that might come in the future. Thank you very much.
Hey, awesome job, everyone. Let's see if there's any questions in the chat. I don't see any, but I was wondering, what other historical figures would you like to train this model on?
We could use it on many presidential historical figures like JFK or Donald Trump even, I don't know.
I think we consider looking even farther back into, like, say, early religious texts and analyzing the sources of like Christian and Vedic faiths and determining how those originated.
Very cool. Awesome job, everyone. Although I do have a slight quibble. I actually tested out your model on my own handwriting, and it came out as chicken scratch. I'm not even sure how you guys did that. Up next, we have Team AI Zymers. It works written down, who will be presenting on early detection of Alzheimer's disease with convolutional neural networks.
Thank you, Mr. Bakir.
Hello, everyone. I'm MehtA, and I'm a rising sophomore at the Hotchkiss School in Connecticut.
My name is Abigail, and I'm a rising junior at Nashua High School South in Nashua, New Hampshire.
I'm Mira. I'm a rising freshman at Belmont High in Massachusetts.
Hi, my name is Maya, and I'm a rising senior at Belmont High in Massachusetts. And our presentation is early detection of Alzheimer's disease with convolutional neural networks.
What is Alzheimer's? Alzheimer's is a progressive fatal disease that shrinks the brain created by a loss of function in the brain cells of connections. It is the most common cause of dementia, and it's the 6th leading cause of death in the United States. It is a major nationwide problem with an estimated of $277 billion in 2018 spent on managing medical and social welfare of 80 patients in the United States alone. Early diagnosis is key to combating this disease and could save an estimated of $7.2 trillion in medical and care costs. What causes Alzheimer's? The brain has 100 billion cells, and they're connected to perform specific functions. These connections can fail, resulting in a loss of function. The destruction and death of nerve cells causes memory failure. The risk factor of Alzheimer's depends on the patient's age, family history, and genetics. Personally, my grandmother has been going through the disease for the past 4 or 5 years, and our main aim is to make the process of detection faster and more efficient.
So the most common approach for detection is noticing mental decline, but unfortunately at that point, Alzheimer's will have caused serious brain damage. So imaging is among the best approaches for early detection of Alzheimer's disease. And while the progression of Alzheimer's does cause brain shrinkage can point to other conditions other than Alzheimer's disease. So having a model that classifies the stage of Alzheimer's based on images would help us be able to detect mild shrinkages in certain regions of the brain that may be signs of Alzheimer's. And so the models that we experimented on detect abnormalities that allow for early diagnosis of Alzheimer's. So there's currently no cure for this disease, but early detection can result in better management of symptoms and prediction of disease progression. So the data set that we use consists of over 6,000 MRI images of the brains of 150 subjects aged 60 to 96 who were each scanned at least once, and they were all right-handed. These images were classified into 4 classes: non-demented, very mild demented, and moderate demented. So one of our limitations was that with the data was that even though 6,000 images might seem like a lot of images, it really isn't a sufficient number to train the model for a high accuracy. So we had to augment pictures using an image data generator, which zooms and reflects images to add more data and to balance the data set.
In both our first and second model, we used convolutional neural network CNN architecture to detect Alzheimer's using images of the brain. Detected into those 4 categories, we varied the number of layers and to increase the accuracy of detection. Model 2 used generators instead of lists to use data and store it, and used it to augment images to make the data set bigger so the CNN had more images to train on and improve accuracy.
Model 3 was a modification of the famous VGG16 CNN, which is a model known for being highly accurate for image classification. And then we trained it on augmented images that were either zoomed in or reflected, and those images were created using generators. And Model 3 ended up being our fastest and most accurate model. So to summarize our results, Model 1 had a test accuracy of 55%. Our overall observation was that this model was slow and computationally expensive, and also had a low accuracy. And this was because of using lists instead of generators. Model 2 had a test accuracy of 60%. This was faster because of the use of generators and more accurate because of training on augmented images as well. And Model 3 had a test accuracy of 71%, and this was the fastest and most accurate model. with the use of the complex and powerful architecture. So what this means is from Model 1 to Model 2, and then from Model 2 to Model 3, we were able to increase accuracy for dementia classification by adding image augmentation, generators, or powerful architectures. Similarly, with a larger, more balanced data set and more image augmentation, we can make models with higher accuracies. By making these changes, Model 3 can serve as a basis of a model that can help doctors in diagnosing Alzheimer's disease early on and improve the livelihoods of millions of people. Thank you.
Amazing. Let's see. Are there any questions? Okay. I don't see any. I have to say, truly magnificent and truly puts the brain in big brain. And spoiler alert, I'm not just saying that because you're my team and you're my favorites, but next up, we have Team Deep Learning COVID-19 presenting on sentiment analysis on COVID-19 related tweets. Let's take it away.
Thank you for the introduction. Our group worked on sentiment analysis on COVID-19 related tweets. My name is Dominic. I live in Natick, Massachusetts, and I am a rising freshman at Natick High School.
My name is Ariana. I am a rising sophomore at Evergreen Valley High School in California.
I'm Claire. I am a rising junior at North Allegheny Senior High School in Pennsylvania.
I'm Hershini. I'm a rising sophomore at Acton-Boxborough Regional High School in Acton, Massachusetts. Our motivation: the coronavirus or the COVID-19 pandemic has caused social distancing and lockdowns all over the world. During these times where there's lots of panic and confusion, social media tends to be a massive source of communication and also serves as a resource for people to share their opinions. Determining the sentiment of social media users through their posts can be a very valuable source during this pandemic because health officials can make informed decisions based on this data. The social media platform that our group explored for this project was Twitter, which has had a 24% increase in daily users during the COVID-19 pandemic. Our objective was to not only find the sentiment of the users through their tweets, but to also compare the sentiment and tweet location to the locations and severity of the virus in different places in the US at given dates. Because many people tend to suspect the government of concealing case numbers, this project provides a way to use the correlation between sentiment and COVID-19 cases to predict the number of COVID-19 confirmed cases. Using this correlation, we were able to compare the number of COVID-19 confirmed cases at a given date and location through the sentiments of tweets in the area.
Our group used two data sets. The first was an IEEE coronavirus geotagged tweets data set, which was made up of over 320 million tweets in English. The second was the Johns Hopkins CSSEG land data COVID-19 data set, which had confirmed deaths and the people tested in it.
The data we received from the geotagged tweets consisted only of tweet IDs. So we first had to hydrate the tweets so that we received the tweets themselves and their corresponding sentiments. We then extracted tweets from the United States and then further separated them by state. Afterwards, we took the tweets and lowercased all the words, removed stop words such as a, but, also, and removed punctuation, apostrophes, and single characters. Then we converted numbers and emojis to their corresponding words and lemmatized the words, meaning that we removed any endings so that words were returned to their base. The attached sentiments range between -1 and 1, and due to an imbalanced data set of mostly neutral sentiments, we polarized sentiments between -1 and -1/10 to -1, representing a negative sentiment, and for sentiments between -1/10 and 1/10, they became 0, a neutral sentiment, and those between 1/10 and 1 became 1, a positive sentiment.
After pre-processing, we used TF-IDF to reduce the weights of the more common words, and also our features were the tweets and our labels were the sentiments. We ran many different models to try to find one with the best accuracy. We started with logistic regression, and after running many C-values and P-values, we found that the C-value of 1 and the P-value of 1 had the best accuracy of 43%. After we used a support vector machine with a linear kernel, and after running through many values of C, we found that the best accuracy was when C was 2 with an accuracy of 42%. Next, we used naive Bayes, and after running through multinomial, complement, Bernoulli, and Gaussian naive Bayes, We found that Gaussian naive Bayes had the best accuracy of 40%. And finally, we used the stochastic gradient descent model with an accuracy of 42%. Since our logistic regression model had the best accuracy, we plotted out the average sentiment per day in the scatter plot you can see on the right. On the left, it's the average COVID-19 cases per day. We can see that there is a possible inverse relationship between the sentiment and the confirmed cases, but we definitely need a lot more balanced data in order to be able to confirm that.
For future research, we would likely take a larger and more balanced data set and apply that to the model, and hopefully be able to form a mathematical relation between the sentiment and confirmed cases. Thank you everyone for listening.
Amazing project, guys. I don't see any questions in the chat, so we'll keep going. I will have to say I love your program because it might help prevent viruses this time rather than a computer program that causes viruses. I would love to see if you could make a tweet bot that then tweets out your results, and then someone else can train a model on those tweets, and then someone else can create a tweet bot from those. Wait, sorry, I'm going too far. Our next team, Team ML-NOMA, up with deep learning techniques for melanoma classification.
All right. Hello, everyone. We are ML-NOMA, and our project was on classification of skin lesions as benign or malignant cancer. I'm Isabel. I'm a rising senior at Middlesex School, and I'm from New Hampshire.
I'm Minnie. I'm a rising sophomore from West Lafayette High School in Indiana.
I'm Preeti. I'm a rising senior at Doherty Valley High School from California.
A rising senior from Al-Ittihad Private School in Dubai.
Our group was motivated to create a project related to healthcare. So we focused on melanoma, the deadliest form of skin cancer, as it can spread very rapidly to important internal organs. Melanoma is caused when genes that control melanocyte cell growth mutate, leading to the cells growing out of control. Though the rarest form of skin cancer, it's also the most aggressive, so early diagnosis is imperative. Deep learning classification of melanoma as a novel form of early diagnosis can increase survival rates, as patients with concerning skin lesions can use our program as a tool to determine whether or not to see a dermatologist. Many current deep learning methods to classify skin lesions only focus on using traditional CNN image classification without taking additional factors such as anatomical site and age into account. This presents a huge drawback as it ignores large factors dermatologists take into account when diagnosing melanoma. So to solve this, our group included these features along with our image data in order to improve classification integrity.
The dataset we use is the 2020 ISIC dataset, which contains two classes, malignant and benign. Each class has images and their associated metadata. If you look at the bar graph, you can notice that So if you look at the bar graph, you can notice that data imbalance is an issue with our dataset, as malignant images compose only 1.76% of the dataset. So to combat the data imbalance, we use image augmentation. Other approaches to image augmentation that we studied forgot to take into consideration keeping the label's integrity. That is, whether or not the augmented image can safely be diagnosed. An example of this is color augmentation. Improper use of color augmentation can negatively alter accuracy, as the classification of the modified image is endangered. Our approach to image augmentation is hair augmentation, a safe form of augmentation that guarantees the label's integrity. So if you look at the figure, you will notice that hair augmentation works by creating duplicates of the original malignant image and randomly concatenating strands of hair onto duplicates, thus combating the data imbalance by producing more malignant images.
Okay, so we represented 9 additional features in our metadata, such as gender, age, and anatomical site of the skin lesion by using a one-hot vector. We also normalized age to be in the range of 0 to 1 so that there wouldn't be too much variance. And the last 7 positions represented the anatomical locations. This pie chart represents anatomical site. This shows that the majority of the skin lesions are located on the torso, so we can see that anatomical site is an important feature to include. We have two different types of models. While both models outputted predicted class, our first type of model was unimodal and inputted only images into a CNN with either ResNet 18 or VGG 16 architecture. Our classifying infrastructure on top of the CNN consisted of 3 fully connected layers and had an activation function of log softmax, resulting in 2 outputs. Our second type of model was multimodal, so we concatenated both the images and the metadata side by side. The classifying infrastructure included 3 fully connected layers and had an activation function of sigmoid, resulting in 1 output of either benign or malignant.
For our experiments, our state-of-the-art multimodal model yielded an average 12.15% increase in accuracy from the unimodal model. In addition, using ResNet 18 produced an average 9.81% increase in accuracy compared to VGG 16. From our confusion matrices for our unimodal and multimodal ResNet 18 models, we saw that the most common error our model made was classifying a benign lesion as malignant, also known as a false positive. And this is the ideal error to make, as it's better to be safe than sorry when classifying the malignancy of a lesion. Additionally, we implemented a GradCam algorithm to see which areas of the lesion the model was using to predict malignant or benign classification. We can see through the following images that ResNet 18 more often uses the area surrounding the skin lesion to determine a classification than VGG 16. Now we'll be showing a sample of our results, which can be seen on our website. If you click on paper/code. And so we inputted 2 images, a benign and a malignant, into our model. And we can see whenever we do have a benign image inputted, like here, our model produces, it says, our model predicted your skin lesion to be benign. We recommend you still see a dermatologist to be safe, but it's likely that your lesion is non-cancerous. And if a malignant lesion is inputted, our model says, we predict your skin lesion to be malignant. We recommend you schedule an appointment with a dermatologist so that you can receive the proper care as soon as possible in the case of true malignancy. So thank you everyone for your time.
I'm seeing a question in the chat, which I'll answer. The question is, did you use images with variable skin tones? So unfortunately, we did not, because the data set that we found were of majority light-skinned people. And this was an issue we found when searching for data sets, is that they were not diverse populations. However, people with more melanin in their skin are less susceptible to getting skin cancer. So in the future, we could create another model, test it on hopefully another model with a more diverse data set, but testing first on majority white skin lesions would be more useful because it represents the majority of the population that has skin cancer.
Great question, and thank you for the answer. And also thank you for the comment. It says, check out Brown Skin Matters for more diverse skin images. So that's definitely a great thing to keep in mind and a great data set. We've talked a lot about making sure that our algorithms are free of bias and trying to get data sets that are more robust. I really appreciate it. And Haripriya, did you want to show a paper? We're going to take the time briefly to share a sample paper. So let's take a brief pause between presentations here for that.
Yeah, in addition to creating a poster and a presentation for the evening, students also wrote a paper and created a website and uploaded their code to GitHub repository. So I want to share a paper. Each of the groups have written a paper. I just want to share an example one here. So hopefully you can see this. Can we see this? Okay, yeah. Awesome. Yeah. So this is, for example, deep learning techniques for melanoma classification. So the group we just saw, you can go and see like all the some things they wrote about first discussing the intro, the methods of what they did, related work, the data set they used, image pre-processing, image augmentation model. So it goes into depth on what they just discussed. The experiments, the results, and the interpretability, which is extremely important. We talk about it all the time. Why does the machine learning model predict what it predicts? And then the future work, conclusion. So I would really encourage you to check out your students' papers after their presentation here.
Awesome. Thanks again. And I have to say that was a very wonderful project. It just completely blew me away. I learned a lot. And I'm not just saying that because, again, you're my group. The pictures, though, really encouraged me to put on some sunscreen. So does anyone know if they sell any with like SPF 5000? Okay. Give it up for our next group, Team GAN-Masters. They'll be presenting on their project, the imitation game, style transfer generative adversarial networks for non-grand chess masters like me.
Hello, I'm Noah. I am Noah from a rising junior at Maine South High School in the Chicago suburbs. And I'm with
Gustavo Salama from Pembroke Pines Charter High School, a rising senior in Florida.
I'm Jeffrey Wang. I'm a rising sophomore in Hopkinton High School in Hopkinton, Massachusetts.
I'm Matthew Michaels, a rising freshman at Proviso Math and Science Academy in the Chicago suburbs.
So today we are going to be telling you about our paper and our project, The Imitation Game, which is about an ST-GANs-based model about the style transfer of chess moves. So now Gustavo is going to tell you about our motivation behind all that.
So the motivation behind creating this AI came from wanting to be able to play my grandfather, who taught me how to play chess after he passed in the future. Along with that, I also wanted to be able to play my friends in chess online, but when they were offline. So I thought it would be interesting in order to create an AI that could copy one's playstyle who's not a grandmaster, so you can play against them whether they're offline or you just want to play against their certain playstyle. To explain the methods taken to create this AI, I'm going to hand it off to my good friend Noah.
So as I had said before, our model is actually an adapted model based in ST-GANs, although our model is actually a little unique from the other groups here as it has two parts. So we have a discriminator and a generator. The discriminator tries to guess what moves the generator has made, and the generator tries to make moves that trick the discriminator into thinking it didn't make those moves. And so every time the discriminator guesses wrong, it gets changed, improved, and then next time it's better at guessing what moves the generator has made. And as if the generator generates a bad move that the discriminator guesses, the generator gets tweaked. And so next time it'll generate a move that that player is more likely to make. So now Jeffrey's going to tell you about more of the experiments we did with our model.
Yeah, so for our experiments, we modified the loss function of the model by changing the variable k within the loss function. And the variable k defines the amount of punishment the model gets. So the greater the k value, the greater the punishment. And each time we modify the loss function, we train the model with games played between Gustavo and his friend Emilio. And then we saved the model. And then we had Gustavo play against the model to see how well it imitated Gustavo's friend. And in total, we modified the loss function 10 times. And so we had 10 different saved models. And so now Matthew will discuss our results.
Our results we found were, as the intensity of the losses increase, the model imitates the subject better, reaching the best balance between strategy and style imitation between the k values of 6 and 7.
So now I'm just going to go ahead and demonstrate the AI in action. Everyone can see this, correct? All right. So here we have the board, and I'm just going to go ahead and open with a very famous, opening. And something to note, Emilio likes to use Petrov's defense, which is basically to bring out the pawn here and one of its knights out here in order to gain more reach around the board. because I like to go for a scholar's mate against him. So if I go here, bring out my queen here, usually I like to attack this pawn with a bishop here in order to go for the scholar's mate. But right now that is not the case because he can still take me as I do not have protection. So I'll just bring out my bishop now. 1, 2, c4. And then here comes the knight. So you can see here, it's trying to imitate his playstyle by using Petrov's defense. And then there goes the other knight. So if I just continue going, he likes to bring his bishops here and then usually go for a castle here. So here comes, so here we go. This is a good example of how the bot is trying to use a more strategic playstyle while still trying to copy his playstyle, as it's attacking my queen, and I still have it protected, but I have to get it out of here. And nothing's attacking the knight. And it just keeps moving its pawn up here to protect its knight. And it hasn't brought out its bishops, which I thought it would do, and then castle. So I thought it would do that, but it's just going for a more strategic approach while still trying to copy its playstyle. Thank you so much for your time.
Awesome job, guys. We have a question in the chat. Gustavo, who wins most of the time, you or your friend? And will this help you to beat him even more?
Sorry, what was the first part of that question?
Who wins most of the time, you or your friend?
Me.
And you think this can help you to beat him even more?
Yeah. I mean, I think so. I should make one about the AI for me so he can try to beat me sometimes,
That's a great idea. I have to say, I love the project, and I especially love the name of your project, the Imitation Game. For those of you who are unfamiliar, it's actually also the name of a paper by Alan Turing, the father of theoretical computer science and artificial intelligence. In fact, it's one of the first papers ever written on artificial intelligence. Also a great movie about him, even if not completely historically accurate. So please check that out. And I also have to say, I would love to play against that model, but honestly, it doesn't take artificial intelligence to beat me in a game of chess, or really any intelligence. Okay. Next up, our only group to list themselves on the New York Stock Exchange, Team NYSE TMS. You can use their ticker tape symbol TMS to go long on them, but I wouldn't bet against them. They'll be sharing their project on sentiment analysis and stock price prediction, and investigation of a tweet-based data set.
Hi, so our project is sentiment analysis and stock price prediction, and an investigation of a tweet-based data set. My name is Srijan, and I'm from Florida, and I'm going to be a rising sophomore at American Heritage.
Hi, my name is Tanushree. I'm a rising senior at Rickards High School, and I'm from Florida.
Hi, I'm Michelle, and I'm going to be an incoming freshman at Carnegie Mellon University. I'm also from Florida. So our motivation for this project was that we wanted to see what can be used to predict stock prices, since most of our parents have gotten into stocks during this quarantine, and especially during this time, stocks have been very volatile. And ultimately, stocks are affected by human emotions. So we decided to identify relationships between public sentiment and stock prices. So we generated a model that takes in both stock market prices and the public sentiment from Twitter tweets, each from the past 10 days. So you can pick how many days in the past that you want to collect data for to predict the subsequent day's opening stock price. We used 2 data sets, one of which was the Twitter data set, where we extracted 60 tweets per day, and our time frame was July 15, 2019 to July 8, 2020. We used a module called Twint to scrape for the tweets and collected the tweets with the keyword, the $sign, and then the company stock label. So for example, Blue Apron would be the $sign and APRN. This module put the tweets into a pandas data frame. So we dropped the unnecessary columns, so we only kept the date and the tweet. The second data set we used was the Yahoo Finance data set, where we focused on only the opening and adjusted closing prices, as well as the volume. We focused on 10 companies, which were Blue Apron, Tesla, Apple, Disney, Starbucks, Amazon, Netflix, Microsoft, Google, and Facebook.
After collecting our tweets, we did our pre-processing. So since the stock market isn't open on weekends and specific holidays, such as Thanksgiving and Good Friday, we dropped the tweets for those dates. Then we tokenized our data, which essentially meant that we took our strings of tweets and we transformed that into smaller parts so that it was easier for our machine to learn. Then for our sentiment analysis, we used a naive Bayes classifier, which is a machine learning model based on Bayes' theorem, which finds the conditional probability of a hypothesis occurring given evidence. This naive Bayes classifier looked at the ratio of each token in positive tweets to negative tweets, and the larger ratio was chosen for its classification. A positive classification was given a value of +1, and a negative classification was given a value of 0. And since not all days had the 60 tweets that we scraped for, all of the empty columns were ignored. To get a single sentiment value for each day, we found the average of these individual sentiment values and assigned that to each day. Then we took our sentiment data set and combined that with our stock data set and then inputted that into our linear regression model. And our output was the prediction of the company's opening stock price for the following day.
Our results show that our model was generally pretty accurate. One metric we use to score how good a linear regression model is the coefficient of determination R squared. And the closer it is to 1, generally the more accurate your model is. Our coefficient of determination, besides one outlier, are generally like 0.99 or 0.97, so they're pretty close to 1. However, we found that our accuracy in predicting whether the price would go up or down wasn't very high. It was generally around 50%. This can be attributed to the fact that tweet data can be kind of noisy and not very representative of public opinion. To combat this, we could use business articles or something more representative of how people who are actually doing the trading feel about the stock market. In addition, instead of using a linear regression model, we could have used a neural net to produce more accurate results. Also, since the stock fluctuates like a sinusoid, we could have used a fast Fourier transform to produce more accurate results. One example to see this code in action is we have the stock prices stock data from Apple from July 17th, July 20th, and July 21st. As you can see, we have the open, the adjusted close, and the volume, as well as the sentiment value that was produced through running it through our code. And we feed 3 days of data in, and we're trying to predict July 22nd close. And as you'll see, it should predict the stock close based on the previous day's input data. It takes a little time to run. As you can see, we got a price of $387.43, and the actual close was $389.09. Thank you for your time.
That was really, really good, especially considering you could generate some results live. That was amazing. I have to say, though, it does make a lot of sense that like even your best performing models were just slightly better than a coin flip, because even the best quant firms don't get it right more than 54% of the time. But that said, they have millions or even billions of dollars to spend, whereas I have thousands of dollars, or not even actually, I just have $1. I'm just lying. But I wish you had told me this information about the accuracy before I went all in on shorting Tesla. I'm just kidding. I would never do that. Please don't do that, guys. Don't take financial advice from me. Okay. Next up, we have Team Fresh Pages, who will be analyzing authorship of the disputed Federalist Papers using unsupervised machine learning.
I just want to make sure, is my audio clear?
Yes.
Okay. Good morning or good evening. I'm Ishita, going into 12th grade at Pembroke Pines Charter High School in Florida.
I'm Satvik, a rising 11th grader at American Heritage Plantation High School in Florida.
Hi everyone, I'm Alice. I'm a rising 12th grader at Stuyvesant High School in New York City.
Hello, my name is Sushant, and I'm a rising 10th grader at Pembroke Pines Charter High School in Florida.
Today, we present to you our research on the controversy of authorship for the Federalist Papers using an unsupervised machine learning algorithm for authorship attribution. Alexander Hamilton, John Jay, and James Madison wrote the 85 Federalist Papers in 1787 to 1788 with the goal of swaying New York citizens to support the ratification of U.S. Constitution. As they didn't want their reputation to suffer, these papers were all first published through an anonymous name, Publius. In the years following, Madison and Hamilton claimed authorship for their papers. However, 12 of these are now considered to be disputed since they both declared that they wrote these papers. Our goal is to investigate these papers and to conclude which authors actually wrote which papers. Through the process of authorship attribution and verification, our unsupervised machine learning algorithm utilizes various features and models to effectively predict the authors of the disputed papers. Following, we will explain our methodology, dataset, and results.
Our data consisted of the Federalist Papers separated into two groups, one containing documents with a known author, and one containing the disputed documents. To make our model more accurate, we removed the papers that were written by John Jay, who only contributed a handful of them, as well as papers that Hamilton and Madison co-authored. To pre-process the remaining articles, we made all of them lowercase, then split them into individual words. This allowed us to remove stop words, which are common words in a given language that appear often no matter the topic or author, such as a, but, the, and that. We also removed words that appeared only once, since they wouldn't play a significant role in determining an author's style.
After pre-processing our data, we decided to extract two features, TF-IDF and punctuation frequency. So TF-IDF is a statistical measure of the relevance of a word to its document within a larger collection of documents. We used the TF-IDF scorings of each word to get the weight for each document. Our other feature was the frequencies of various punctuations. We specifically used commas, periods, and colons to further identify each author's unique writing style. We then combined this data to form one matrix and trained a k-means model off of said matrix. Then to find the accuracy of these features in our model, we compared the author labels generated by the model when inputting data from the known papers with the already known authors for each document. Doing this allowed us to narrow down which features were the most useful and which to get rid of. For example, we had tried parts of speech tagging and lexical richness, but since these features resulted in lower percent accuracies, we decided to remove them. We found that the prediction accuracy for TF-IDF alone was 75.76%, and the accuracy for punctuation frequencies alone was 54.55%. In the end, when we combined these two features, we got a prediction accuracy of 81.82%.
Through our unsupervised machine learning method using the analysis of stylistic and linguistic features, we were able to predict the authors of the contested papers. Our final results show that Alexander Hamilton wrote 8 of the papers, while Madison wrote only 4. This indicated that Hamilton indeed wrote the majority of the disputed papers. For further research, there are a number of other methods that could be employed to approach this topic. For example, using a more diverse data set and other features could increase the accuracy of the model. There is also the potential to allow for other authors and their works to be analyzed as well. Effective authorship authentication can also be very useful in a variety of other fields like education systems, criminology, law enforcement, and more.
Thank you for your time.
Awesome, everyone. Thank you so much for that. I have to say, I don't think there's ever going to be any artificial intelligence smart enough to write something as beautiful as the Federalist Papers. That said, I'm wondering if a machine learning model can tell us who wrote the Federalist Papers, will we ever find out what was going on in the room where it happened? Okay, next up is our team Music Gen, who will be displaying their project on music generation.
John.
Sorry, I was muted. Hi, my name is Ben. I'm a rising junior at Christian Heritage Academy, and I live in the Chicago suburbs.
Hi, my name is Lily Basson. I'm a rising freshman at Glenbrook South High School, and I also live in the suburbs of Chicago.
And we decided to make our project music generation based off of machine learning.
So our motivation was kind of based off of, I've always really loved music. And I've kind of had a dream of like pursuing music ever since I was little. So like a music producer would be really cool. But when I found out we were doing a project, my mind automatically went to music, and I thought it'd be really cool to do a project like involving music. So when our teacher kind of told us we could do something around music generation, I thought that'd be a nice fit.
Okay, so for our experiments, so the first thing that we did, we ran the test codes with the MP3 files, and they were called M&M and NumPiano. This is part of the original code which we got our code from. So when we ran this code, the computer ran the songs to create a new song, which was basically 6 seconds long, and it had the first 3 seconds of the 2 songs which we inputted, but it was very blocky. It had the first 3 seconds of NumPiano, and then it went straight into the M&M. So it was very kind of, it doesn't really, I guess it didn't really sound good. So for our model, we use LSTM, and it's actually pretty interesting because we used 2 types of the same LSTM. They're called RNN. One RNN is for the left ear, while the other one is specifically for the right ear. So, so we did that, and then actually, before we started coding at all, this process actually took 1 to 2 days. We made sure that our computers were up to date in the terminal, like we downloaded PyDub, Panda, etc. And we just made sure that our code could be running, and it was running smoothly after that. So yeah, after we updated it and we inputted our new 3 songs, which was Young, Dumb, and Broke by Khalid, Butterfly Effect by Travis Scott, and Make It Right by BTS featuring Lauv. And we played it.
So our results, the songs that he just named, when we plugged them in, they produced like a cool music mashup that took about like 30 minutes to run. It was like a mashup of like the first 4 seconds of each song. So it was like 12 seconds in total. We're still working on making it so that the program will only play the beginning of the song and maybe like the middle 2 or the end, or you can like pick and choose which part of the song it plays. We're also kind of working on trying to teach the machine how to, run between the songs smoother, or maybe play more of the song, more than 4 seconds. Because when you listen to it now, it's kind of a little rough on the ears, kind of similar to noise music. And noise music is just kind of like using like the negative parts of music and using it in like cool or like imaginative aesthetic ways. It's also known as like noise pollution. So we're kind of trying to make our songs more, clean and smoother rather than having it be, rough.
Yeah, so adding on to what Lily said before about us still working on the program. So about 1 to 2 days ago, we tried adding a new, variable into the code, and it's called shuffle. And what it basically does is it shuffles the song, and it's supposed to, make it so that it doesn't just play the beginning. However, when we did this, we just got static as our result, and we don't exactly know why it is, but yeah, it didn't really work out. So we had to stick with the original and take out the shuffling. And so in the bottom right, you can see the RNN summary, and it basically shows you what's happening and kind of, yeah, what it's doing. And I'm actually going to, if I can move this. Yeah, I'm going to show you the song that we created. It's going to be loud, so I guess you should like try.
Warning for headphone users.
Yeah, just
For like take them out, set them on the counter.
yeah. If it's like if you're using headphones or your volume's up, turn it down. So yeah, that's a warning. Okay, so it's RNN. And that's what we created so far. Thank you.
Awesome job. Thank you guys. And I have to say that beat drops hard. I don't actually know what that means. Apparently that's slang. I have to say it is much better than the noise pollution that my mom says I listen to. So up next, we have Team Real versus Fake News, who will be showing us how to detect fake news using support vector machines.
Hi, our project is detecting fake news using support vector machines. I am Jonathan, an incoming senior at Maine South High School in Park Ridge, and my team members are.
Hi, I'm Brad Altman. I'm a rising freshman at Brandeis University. I'm also from the Chicago suburbs.
I'm Rachel Kim. I'm an incoming first-year student at the University of Toronto, and I'm from Canada.
And I'm Rachel. I'm a rising junior at Seneca Valley High School, and I'm from Pittsburgh, Pennsylvania.
News networks and the media have become increasingly popular as technology has allowed for real-time updates on national and international events. However, misinformation is a real problem. When fake news is circulated, it can spread quickly and confuse vast groups of people, in addition to diminishing the credibility of trustworthy news platforms. However, with a vast amount of news articles circulating, it isn't really feasible for humans to check the validity of each individual article, but artificial intelligence can serve to solve this problem, detecting fake news with a high level of accuracy.
The dataset we used was Kaggle's Fake and Real News dataset, which was published by Clément Bissaillon. The data contained the title of each article, the text, the category, and the date published. We used 20,826 real news headlines and 17,903 fake news headlines. The pre-processing steps we took were first to assign numeric labels to each of the news articles, with the number 1 representing fake news and 0 representing real news. We also only took the title and the first 1,000 characters of the text of each article. We then tokenized this, removed all non-alphanumeric characters such as punctuation, removed all stop words or commonly used words, and lemmatized each word to their root word. And the diagram on the right shows a sentence that has gone through this pre-processing steps. The model we used was a support vector machine.
Our group then took that pre-processed data and SVM and put them together. We wanted to maximize the accuracy of the SVM, so we proceeded to experiment with different kernels, C-values, gamma values, and degrees. The graphs below show the results of the SVM with multiple kernels and the SVM's linear kernels and various C-values. What you may notice is that the SVM with a headline and text continually outperformed the SVM with a headline only by around 10%.
For our final headline-only model, we decided to use a support vector machine with a linear kernel and a C-value of 1. We chose this specific model because it had one of the highest accuracies, while remaining simple enough that it wouldn't overfit to the data. Additionally, the simplicity of the model allowed it to be more interpretable to humans. Our final headline-only model had an 89.
Oops, Rachel, I think your mic cut out.
Model for the same reasons stated prior, namely the high accuracy and simplicity. Our final headline and text model had a validation accuracy of 98.07%. We used these models, along with the pre-processing techniques we discussed earlier, in order to create a program that asks for user-inputted news headlines, or news headlines in their corresponding text, and classifies the input as fake news or real news. Here you can see some examples of headlines that our program classified correctly. The headline, GOP Scales Back Convention Plans, Relenting on Virus Restrictions, is a real headline from NPR, and our program correctly classified it as real news. Whereas the headline, Self-Loathing GOP Congressman Can't Believe He's Been Reduced to Defending Necessity of Public Schools, is a fake news article from The Onion, which our program correctly classified as fake news. Here you can see our program, where we load the model and input the headline, DOJ charges 2 suspected Chinese hackers who allegedly targeted COVID-19 research. When we run this model, we see that it correctly classifies this as real news. It's from NPR. Whereas the headline, Trump admits 18 new states in order to increase competition for medical supplies, is a fake news article from The Onion. And when we run it on our model, it correctly classifies it as fake news. Thank you everyone for listening to our presentation.
Hey, nice job. That was a great presentation. Is a headline that I am sure your model would classify as real news, because that was amazing. Okay, up next, we have analyzing supervised learning methods for credit card fraud detection by team Master Fraud Discovery.
Hi, I'm Jennifer, and I am a rising college freshman from South Carolina.
My name is Karen, and I am a rising senior in Vancouver, Canada.
I'm Grace. I'm a rising senior in Yorktown High School in New York.
Every year, billions of dollars are lost just in the US due to credit card fraud. And unfortunately, most of the people who pay for this loss are the sales companies and the credit card companies. So what if we could predict whether a transaction is fraudulent or not ahead of time? And that way we could lower a lot of our losses. So in our project, we explored several established supervised learning models that could be used in credit card fraud detection. The data set we used was obtained from Machine Learning Group ULB, last updated in March 2018. This dataset included 30 feature columns that had the time stamp at which the transaction occurred, the amount involved, and 28 components that basically is the information related to the transaction encrypted by using principal component analysis. And this information is obviously encrypted for privacy reasons. So we have no idea what they mean. And finally, the labels include the fraud and non-fraudulent transactions. And in our whole data set, around 500 of the transactions were fraudulent and 300,000 were not fraudulent. This leaves us with only 0.17% of the transactions being fraudulent.
So as you can see by the graph, our dataset is highly imbalanced. So after our initial train test split, we had a very imbalanced training set and testing set as well. So with the testing set, we want the testing set to be imbalanced so that it can reflect a realistic ratio of fraud to non-fraud. But our training set, we want to balance so that our model is predicting solely based on the features and not also based on the imbalance in the classes. So in order to balance the training set data, we used SMOTE, which generated more fraudulent data points.
The 3 original models we implemented were a decision tree with a max depth of 6, KNN with 4 nearest neighbors, and a random forest with 800 tree estimators. From these 3, we combined them pairwise to get 3 more models. And the way we combined them was if a point were labeled as fraudulent in both of the original 2 models, then in our new pairwise combined model, it would also be labeled as fraudulent. Otherwise, it would be labeled as non-fraud. We also created a fourth combined model, which combined all three of our original models. And in this case, a point would be labeled as fraud if and only if it were labeled as fraud in all three of the original models. As you can see in our combined models, we had a much higher precision rate, over 95% in all four, which is higher than any precision rate in any of our three original models. And our recall rate also was fairly high for our decision tree and random forest.
So each of our models predicted either fraud or non-fraud for each data point, but we wanted to change this binary classification into a probability, and we did this by using the precision rate and the inverse precision rate for each model. So this gave us 7 different probabilities from each of the 7 models. And what we did is we took the maximum of these 7 probabilities in order to calculate our final fraud score. And we did this because we would rather have more false frauds than to have frauds that are predicted as non-frauds. And we evaluated our final fraud score model at a cutoff of 80% probability of fraud. And this yielded a precision of 84% and a recall of 82.3%. So this is actually a good sign because our recall for our final model was the highest out of any of our models. And the recall is precisely what we want to maximize in order to minimize the number of undetected frauds. So since our final fraud score is a probability and it's not an absolute decision, this can allow credit card companies to also factor in their own personal considerations when they're making informed decisions against credit card fraud. So this was our presentation on comparing and combining 3 different supervised learning methods for detecting credit card fraud. Thank you.
Awesome job, guys. I don't see any questions in the chat, so let's keep it moving along. But hold up, give me a second. Oh, sorry. I just needed to make sure my latest transaction ordering $100 worth of My Little Pony merchandise was not marked as fraud. Our next team is Team Interpretis Linguae Latinae, presenting Latin translation with machine learning.
Salvete, sumus discipuli linguae Latinae. Hello, everyone. We are students of the Latin language. Thank you all for coming tonight. I promise we are the last group. I'm Zoe. I'm a rising junior at Proof School, calling in from New Hampshire.
And I'm Summer. I am a rising sophomore from Deerfield Academy in Deerfield, Massachusetts.
Unfortunately, our third group member, Susan, is not here right now. She is a rising senior at Middlesex School and is currently home in Korea. If you are currently learning a language or have recently taken a language class, you may have found yourself wishing you could get a bot online to do your translation homework for you. I know, I have. For most popular spoken languages like Spanish or German, you can use Google Translate. If you're taking Latin, however, you're out of luck. Google Translate for Latin currently relies solely on a statistical model for translation and thus is not able to process complex grammatical structures in varying word order for Latin. The accuracy for Latin is significantly lower than for other languages. In our project, we wanted to create a neural machine translation model that processed grammar, assigned appropriate synonyms, and understood idiom. And most importantly, provided an accurate translation of inputted Latin sentence into English. Our specific goal was to get a translation more accurate than that from Google Translate. So when attempting to create our model, we quickly realized that the main factor in this model's final accuracy was our training data set, and specifically its size and the quality of the entries. In order to address this issue, we included 3 different types of English to Latin translations in our data set. The first type is a vocab list of roughly 13,000 nouns, adjectives, pronouns, adverbs, verbs, and conjunctions. A small portion of these nouns, adjectives, and pronouns were fully declined in an attempt to teach the model the grammar endings, while the remaining were only declined in the nominative and genitive singular cases. And similarly, a small amount of the verbs of all 5 of the conjugations were fully conjugated, while the remaining were only split into their 3 or 4 participles. These vocab words were also each given multiple synonyms. This large vocab list is important to include in our data set because it allows the model to know exactly what each word means, and it increases the overall accuracy of translation. And the next part of our data set is a collection of nearly 2,300 phrases and short sentences taken from common Latin sayings or easier textbook examples. These phrases usually have 2 to 6 words and are useful to include because they contain a very simple grammatical structure and teach the model words that are commonly found together. And finally, our last piece of our data set is over 1,000 complex Latin sentences taken from real classical texts by ancient authors like Cicero, Caesar, and Virgil. And these are generally longer sentences that have multiple phrases or clauses and are written in the classical style, which means that they could have a more complicated grammatical structure or have a scrambled word order. These sentences are useful to include because they allow the model to translate full sentences and analyze a more complex grammar structure.
Yes, so when we are training the data set, we randomly shuffle the data we have and we select 13,000 entries from them, among which 11,000 are used for the training data and the remaining 2,000 are used for the testing data. For the model, we use an encoder-decoder LSTM model, which is really classical for translators in general. And here we trained it for 120 epochs. So here we have some demonstration of the result we have. This column is the predicted result of the Latin translation, and this is the actual Latin translation. So we are pretty good at predicting vocabs and short phrases. As you can see here, it's usually either exactly the same or is some kind of synonym. Like here we have ask, old man, and senior, which is like basically the same thing. And this is another way of getting the predicting result when we like predict the sequence. And I also have this demonstration of the Latin sentence we translated. This Latin sentence we inputted, Aque hac quidem quaestio communis est omnium philosophorum. It literally means, and this inquiry is the common property of all philosophers. And you can see our translation is pretty accurate. It changed n to moreover, which is the synonym thing it usually does. We also have, so when I put this into the Google Translate, you can see the result is, in addition, this is common to all the philosophers and the problem of, which is not wrong because it's like a literal translation of what it is. This is because Google Translates use PBMT, which literally translate every word for its actual meaning. And because Latin sentence sometimes can be a little bit messed up because we don't really have this grammatical structure of subject, word, object, we just sometimes just switch things up. So the translated result in English can be a little bit like messed up and it doesn't make sense sometimes. By using machine learning model, however, the machine can pick up on the grammatical structure and the pattern, so this problem is usually resolved. And yeah, that's it. We are the Latin translation group, and thank you, everyone.
Amazing presentation, guys. And I have to say, beautiful job explaining, comparing your model to Google Translate and how your model beats them. Illa magnum erat. That's Latin for that was great. Thank you, Zoe and Summer, for actually teaching me that and how to pronounce it. That was our last presentation, but certainly not our least. All of our students did an incredible job, so let's give it up for them. A round of applause. You guys can turn on your mics if you want. And I'll turn the mic back over to my sister, who'll make a final announcement, say some final words, and then we'll come back to me.
So I just sent a link in the chat. Here at MehtA Plus Tutoring, we're committed to the open source software movement. So all the students' code is online. Their presentations, their posters, their websites are all there. So I'm going to share my screen and just show you so that after the presentations, you guys can feel free to check out their work more. So we can scroll down. For example, we can see the handwriting recognition group. And you can see all the groups here. We have linked it to the website. We have our abstract here and the team members here. So you can see, for example, that they have their abstract, they have some examples, they have their poster, their presentation video, in case you want to rewatch their demo. They have their paper, the GitHub link if you want to check their repo, and their code. So thank you. If you have any questions or any comments, please feel free to chat it, and we'll stick around for a few more minutes. Thank you.
Habe bonum noctem. Have a good night, everyone. Again, that's Latin. Hopefully, I'm doing you guys proud, Zoe, in summer. I'm just kind of sensitive, but I don't really know what I'm doing. I apologize for butchering the pronunciation. Thank you all so much for attending tonight. Thank you so much for taking the time, supporting your family members and all of our students. And I'll play you guys out. I also want to thank you guys personally from the bottom of my heart, because not only did I get the incredible opportunity of being here and doing 40 incredible students, I also got to finally live my lifelong dream of being a stand-up comic. And sadly, I'll be announcing my retirement from the game tonight as well. But it was a great, incredible opportunity, and I thank you all so much. Let us know if you have any questions, and I'll play us out.